Okay, hello again, everybody. Welcome back. Hope you've got your drink. And we're going to start our final session on grid scale storage with Andre from University of Southampton. So if you're ready, that would be great. Hi.
So yeah, hello. Can you hear me right, Rachel?
I can hear you and see you there. Yeah.
Okay, so I will share my screen just now. Okay. Can you see that?
Not yet.
Oh, okay. Let me try again then. Can you see it now?
Yeah, that's coming up now.
Okay.
Yeah, that's great. Thank you.
Okay. So yeah, hello everybody. So my name is Andre. I'm from the University of Southampton. I'll be talking today about hybrid and dual chemistry battery systems. So this project has been sponsored partially by GSUS and partially by EPSEC. So I want to say that just from the start. And also I'm being supervised by Professor Andy Cruden. And cons on like what are the characteristics of lithium-ion acid. You can see that they are quite complementary. Lithium-ion can provide high bursts of energy, high bursts of power, but again, maybe it's a little bit more expensive, and so on and so forth. So if we couple these two types of batteries, maybe we can get to something we can use at a cheaper cost overall. Right. So specifically, GSUS has a site somewhere in South Wales, and they have a microgrid. So as you can see here, I think, well, if I use this, okay, so, all right, so they have this, the factory and the battery system, and they have a microgrid which has a PV system and a wind turbine. So the battery system is somewhere in here. So I think some people from Sheffield also worked on this project. And yeah, so my project basically has into consideration the battery storage unit only. Okay, right. So this is kind of their system. So, like I've said, it uses two types of chemistries, lead acid and lithium-ion. So you can see in the top right, that's the ADEPT system that I just mentioned about in the microgrid system. On the bottom left, you can see the a system actually which was installed a few months ago in Southampton port, in a Portsmouth port, part of their decarbonization strategy. And there are quite a few other companies offering these kinds of systems in terms of maybe a little bit different, but these kinds of hybrid systems. For example, I've mentioned in the bottom right the BOS company, which is a German manufacturer, and they do lead acid and lithium-ion hybrid systems for small scale, like for home systems or maybe small commercial units. Okay, so yeah, so if we're going to take a look at the GSUS system, so this is a very very simple schematic, an indicative schematic. So it has 4 strings, right? So it has 1 of lead acid and 3 of lithium-ion. You can see here some technical characteristics of the modules. And of course, what is specifically unique about this system is, I think it's unique in the UK actually. When it was first installed, it was the first of its type in the UK. It has a DC connection, so it has no power electronics in between lithium-ion and lead acid strings. So all they have is just some MCCBs between the strings, right? Okay, but of course, yeah, now comes the question, what's going to happen and in terms of behavior when you have a DC connection between the strings. So this is actually what I'm going to talk about, and this is my project, basically trying to understand how a DC connected hybrid system actually behaves and works, and how can we model that. So, well, so how do you model a battery? Well, a hybrid battery basically you take and you model first the lithium-ion cells, and then you model the lead-acid cells. So you can see in this picture, I've shown the things you can do in terms of modeling that. I'm using, of course, the equivalent circuit theory. This is kind of at the pack and cell level. So you can see you have different resistances for collectors, and you can talk about charge transfer resistance and all the diffusion elements for the electrolyte and for materials and the active materials and so on and so forth. So you can see, for example, that you can build an equivalent circuit, which is this one. I'm not going to go into all the derivation, but you can derive this kind of circuit, which uses two RC groups, which models quite well the both lead acid and lithium-ion cells. Again, I've said I'm not going to go into all the details, but this is kind of what I'm using at the moment. So how do we do this, right? This is basically what we need to see. If I go back a little bit, so all we can do is just like try to match the data, the experimental data with the simulated one, and try to fit these parameters in terms of obtaining a better experimental fit for the data that we're obtaining. So, for example, in this slide I've shown with the red the red curves. If you look on these graphs, are they similar? On this one in particular, the red is the experimental one, and the simulated one is the blue one. And the simulated for the lead acid, you can see in this slide, is the red curve, and the experimental one is the blue one. So I'm not going to go again into details on how do you extract all the parameters, because that's another presentation, but this is how basically the process. You take the experimental data, you fit into everything into a MATLAB model, you use an optimization tool, and basically match the experimental data with the simulated model. Okay, so you basically end up with something like this. So this is fundamental for you to understand of what I'm actually doing. So if you look at this system, so basically you have one lithium-ion string and one lead acid. So if you imagine multiple groups of RC groups all connected in series, you kind of end up with this kind of configuration. So the question is, what's going to happen when you apply a pulse to these kinds to these two strings? So first, what's going to happen? You're going to have the initial current is going to go through the path 1, basically because C1 and C2, the capacitors, is going to behave like a short circuit for a very small short pulse, and then slowly the capacitor is going to charge, and eventually the current is going to flow through the R1, R2, and R0. So if C1 and C2 are different, we're going to observe that they are different. We're going to obtain a very nice effect in there. So if you look at this, right? So this is what I was talking about. So if you apply pulse, this is kind of a generic discharge pulse, which I've applied on my model. So you can see that initially, if I take only the top curve is for the lead acid string, for example, you can see you have a drop of voltage. Then between, for example, B1 and C1, you have another slow because of the capacitors. The capacitor starts to charge, so you have another extra drop because the current starts flowing to the R1 and R2 instead of just C1, C2, and R0, and kind of reaches point C. And then when you stop discharging, the current, the voltage jumps back to point D1, for example, and then slowly recovers between D1 and E1. Okay, so the same for the lithium-ion string, but you can see that they are different, right? You can see that the curves are different, which means that the capacitors for lithium-ion model, they're bigger, they're larger. So for example, I've just written here a very small indicative equation. So you can see that for lithium-ion, C1 is 1.6, the average C1 capacitor is roughly 1.6 of lead acid, and for C2 capacitor, that's kind of, for lithium-ion, is kind of almost 6 times the lead acid ones. So you can see that they are different, and this kind of creates this this effect, right? So if you look at this figure, you can see that initially, if I apply 50, and this simulation is for a 50 amp pulse. So you can see that the initial current, right? The blue one is the lithium-ion string. The initial current through the lithium-ion string is bigger than the lead acid, but slowly after a while, because the current is eventually going to go through path 2 for both strings, you can see that eventually lithium-ion lead acid string is going to provide a bigger current than lithium-ion. And then when I stop discharging, you can see that what happens between point C and B is like the lead acid string is charging the lithium-ion one. You can see that's happening in point B. So again, what I'm trying to do, I'm applying a pulse train discharge of 50 amps. So you can see these kinds of effects. And basically that happens because the capacitors C1 and C2 and R1 and R2 are basically different, right? I'm not going to go again into much detail, but this is the main point of what I wanted to present to you today, is how this happens when you have a DC connected hybrid system, right? So we can start asking questions now in terms of how this affects the efficiency, how this affects the overall power, the current sharing between the two, because you can say, right, if I apply a very narrow pulse, you can see that, for example, most of the current comes from lithium-ion, for example, basically lithium-ion taking the heavier load, let's say. But if you apply like a constant discharge current, then that's going to be different. Okay, so if you got that, that's the main point which I wanted to show you today. So what conclusions can we draw from this? So first, of course, in hybrid systems where we have transient effects, and of course, this, like I've said, this cannot be ignored when you have very large systems like we're talking about. So again, the second conclusions I would say is like all of these currents, which I've shown you before, previously in the previous slides, it's because they have, the batteries have different dynamic effects, basically have different voltage profiles because of different diffusion coefficients and stuff like that. Okay, and of course we have the energy transferred between the strings. If, like I've said before, if we have a pulse train discharge, then we're going to have on each pulse we're going to have some energy discharging from lead acid to the lithium-ion string, and then to the load. And how much are we talking about? So, for example, I've introduced here a small example. So, for a 50 amp discharge train pulse, let's say with a period of 60 seconds and 20% duty cycle, well, the energy can be around 22%. Well, the energy transferred between lead acid and lithium-ion string can be around 22% of the total discharge energy, right? And yeah, the last one, which is quite interesting. So it's not necessarily obvious that these kinds of energy transfer between lead acid and lithium-ion and vice versa is necessarily going to decrease the energy efficiency. And why? That's very interesting because yes, you lose some charge because of the Coulombic efficiency, right? It's not good to charge and discharge lead acid batteries because you lose, of course, you lose energy. But in the same time, if you get some energy from the lead acid string into the lithium-ion and then discharge into load, what actually happens is because the lithium-ion battery has a lower resistance than lead acid, then yes, you lose some charge because of the Coulombic efficiency, but you have lower ohmic losses. Basically, you have the same effect as when you have a supercapacitor connected in parallel with the battery. Battery connected in parallel with a supercapacitor, right? So hopefully that was clear and at least maybe a little bit interesting for you. So yes, thank you very much. If you have any questions, I will be happy to answer. Thank you.
Okay, thank you, Andre. Again, if you've got any questions, can you pop them in the chat there? I thought that the way you'd laid out that equivalent circuit over the top of the battery was a really nice way to present it. I've not seen it done like that, and it kind of brings it together, gives it all a bit more meaning. So that's rather nice. In a practical application, do you know whether people do allow the lead acid battery to charge lithium ion, or do they prevent that happening? Do they have diodes in there to prevent
Right.
the...
So yeah, right. So for example, the GSU auto system does not have, or they have some switches which kind of at some point manages well when to discharge lead acid and lithium ion, but they don't have any diodes. They kind of let them wild in a way.
Yeah.
So that's why I'm doing this research, because they want to know how much energy losses are we talking about and how bringing all of this together. So that's why I'm doing the research.
Okay. Yeah. And have we got any other questions for Andre? Okay, we haven't got any here at the moment. So Thomas, if you're ready, Tom, then we could probably move on. We actually don't have our final presenter today, Mehmet. So I have asked Sol to do the wrap up a little bit early. Hopefully he'll be ready to do that by then. So, but I'll hand over to Tom now, and I think he's going to talk about safety for laboratory testing of lithium-ion battery packs.
Yeah, that's right. I'm just getting the slides up. Great. So hi, everyone. I'm Tom, and I'm a PhD student at the University of Sheffield, part of the Energy Storage CDT, and I'm supervised by Dan Gladwin. Today I'm going to be talking about an overview of safety for laboratory testing of lithium-ion batteries. Might sound a bit boring or heavy for the last one of the conference, but hopefully I'll try and make it a little bit interesting. So just a little bit about what I do in my PhD to start with. So my PhD work concerns modeling large lithium-ion batteries. So by large, I mean multi-cell packs with tens to hundreds of cells in series. And my research is around sort of improving how the battery models for these larger batteries, my research is around improving the battery models by giving these large batteries, by giving the model a view of the individual cells in the batteries. So the model knows what's going on inside. And I'm generally looking at electricity grids as the application. And as with all modeling, it's really important to verify the models with experimental work. So I'm involved with a lot of battery testing in our research group. And we're testing both cells and battery packs. So that'll be from tens of watt hours, so like the 18650 you can see in the picture on the left, up to 2 megawatt hours, 1 megawatt hour, 2 megawatts battery packs, such as the Willenhall energy storage system there on the right. And the work I'm presenting today is a bit of a side project that stems around this question of, are lithium-ion batteries safe, or can we safely test them? So we certainly know that lithium-ion batteries can be dangerous. I've just got a few high-profile incidents to share with you here. So the Samsung Galaxy Note 9, about 1 in 75,000 of those batteries had a defect which made them spontaneously combust. Just for reference, the normal sort of defect rate is about 1 in 10 million. 10 million is what I found. Also heard about the Boeing 787 high-profile incident where a lithium-ion battery pack had an internal short circuit, as in the pack had the defect this time, not the cell, causing them also to combust. And we've probably all seen the pictures of Teslas on fire, with reports of them being very difficult to extinguish. So how about for lab testing? Is that safe? So on one hand, in lab testing, the environment is much more tightly controlled. So there's much lower risk of like debris puncturing a cell, which might be higher in a car. But on the other hand, there's typically fewer safety features shipped with these prototype batteries, and you might be using custom charging setups and that sort of thing, making them more dangerous. So in the research group, we unfortunately know firsthand that lab testing can be dangerous. So I'm going to talk about an incident we had. I'll say now it wasn't me, but there we go. So to start with a few details, there was a research testing a 20 amp hour lithium titanate cell. Looks a little bit like that cell to the right. They're performing EIS, so measuring the impedance of the cell at 10% increments of charge. So that involves charging and discharging the battery in 10% steps. They're using off-the-shelf equipment from a well-known, well-respected manufacturer, and it's definitely worth noting that the work was suitably risk assessed and the researcher was well trained and knew what they were doing. And then one last thing that's important is that the test was 30 hours long, so it had to take take place partly overnight. And what happened is during one of these charge steps, the software that was controlling it crashed. That meant that the testing machine continued charging and ignored the voltage limits that were set. So it overcharged. And instead of describing what happened, we managed to capture and recover CCTV footage. So I can show you that. Let's just get the laser pointer thing. So if you keep your eyes down here, there's like an environmental chamber just at the bottom here where the battery is being tested. And I'll just play that now, and you can see what happens. So yeah, there's a bit of an explosion. Room's quite quickly filled with smoke, lots of flames. Yeah, I don't think I said this. This is overnight. This didn't take place during the day. It was when no one was here. So yeah, and then if we fast forward maybe 3 or 4 minutes, I'll play it there. Yeah, you can see the flames have now sort of taken hold, and the room is very much filled with smoke. So what are the consequences of that? Well, the fire brigade were called by university security, who had responded to the fire alarm, and they came and extinguished the flames. The equipment close to the fire was damaged by the flames, and the rest of the equipment in the room was damaged by smoke, soot, and the copious amounts of water used by the fire service. This meant that everything in the lab had to be disposed, but fortunately everything other than the cell that was research critical had their experimentation work had finished, so we got away with there. This resulted in £250,000 of an insurance claim, which is kind of good because it means that we didn't have to pay for it, but you know, insurance claims up the premium, so I hate to think what the premium is now, but I don't pay it, so that's fine. And then I guess the biggest sort of consequence from my perspective was that we had to stop battery testing for about a year while investigations were taking place. And we really don't want it to happen again, hence the motivation for doing this work and researching how can we test as safely as possible. So the current research, or the research that's out there in battery safety, is generally around the safety of a cell. So it's very well understood how cells behave and how they fail. So, you know, overcharging, over discharging, it says they're short circuit, but that could also be like overcurrent just from a poorly managed test. A thermal overload, so it says external there, but could also be internal, as in, you know, if you're generating too much heat in the cell. Some sort of mechanical impact or just an inherent defect in the cell, which results in two things: either the cell fails happily and we're all safe, or the cell will rupture and will thermally run away. Lots of smoke, fire, and bangs and whistles. This is helpful, this research, in knowing what we're trying to avoid, but obviously it doesn't consider the failure of a whole battery system and doesn't necessarily talk about what the underlying causes of these things, which is where my work's come in. So I've undertaken a failure modes and effects analysis. Short FMEA is that shortened, and I've done FMEA on lab testing specifically rather than in another application. FMEA is an engineering approach, and we can use it to find the most likely failures and the effects of those failures. So it's a bit like a very detailed risk assessment, which we then use to inform where we're going to focus on extra safety precautions. Yeah, so this is the typical setup that that would be used for battery testing. On the left here we have if you've got like a multi-cell pack, and on the right here we've got if you're just testing a single cell. So typically if you're testing multiple cells, you'll have battery modules. They will be connected in series or parallel, and each one will have a monitoring board which will monitor things like voltage and temperature, which then gets reported back to a central battery management system. That will then communicate with the PC, which does the controlling, and the PC will also control the power supply or load, or in this case bidirectional power supply, which powers the batteries. Very much a similar story for cells, except there's no BMS because the power supply does the voltage measurements and current measurements. So then back to failure mode. So the key findings we had from that. So as we already know, in general, the aim is to prevent a cell reaching a limit, either voltage too high or too low, temperature too high, or current too high. So then generally, these battery systems are controlled by software, and failure of the system as a whole, i.e. one of these limits being reached, is most likely due to the failure of the software. That might be poorly written code or failure of the communication between different systems, such as the BMS and the power supply, and whatever, the PC that's controlling them. In addition to those, there's quite a high likelihood of failure when physically constructing the system, or maybe transporting it. For example, like a short circuit from metal tools you might be using, or damage from like dropping a pack. So then, after we've done that FMEA, we can think, what do we do to reduce the risks? So this is what I've come up with. Firstly, we can reduce the likelihood of a cell limit being reached. So that might be through good experiment planning. It's a bit of a wishy-washy term, but I'll try and explain it now. So basically, the actual experiment shouldn't exceed the limit, like the voltage limits, and the software that controls it should be actively preventing voltage, current, or temperature limits being exceeded. So assuming nothing goes wrong from a software perspective, it shouldn't be possible to exceed any of the cell limits. And to do that, the software should control the power supply to stop the current, should it detect any problems. So they've written independent protection systems, so sort of additional systems that are independent of the software or communication that's going on. So that could be a system which can open a contactor should it detect a limit being reached. That could be the BMS controlling the contactor, or a separate protection circuit if you're testing single cells. And another sort of system is a fuse. So a properly rated fuse can protect you against overcurrent and can easily be replaced if an incident occurs. And then the last way to sort of reduce the likelihood is good practice. Again, a bit wishy-washy, but I think to go into more detail, that means using insulated tools, or being sensible about where you're running cables, making sure they're not going to get pinched and cause a short circuit, that sort of thing. And then secondly, we can try and reduce the impact or the severity if all these safety measures fail. So that's either containing a failure in a fireproof enclosure, or attempting to extinguish any flames and remove heat using fire suppression. And for fire suppression, that could either be an automated canister system or a sort of handheld lithium battery specific fire extinguisher. Okay, so looking back to those system diagrams, so firstly for the single cell, this is what the new system diagram is. If you're implementing all of those mitigations. So we've got our fuse and contactor, which is being controlled by this external protection system. And that system is measuring temperature, voltage, and current. And just a bit of a closer look at that. So inside, I designed it to be completely analog, so this all uses comparators and latches. So the comparators take in current, temperature, and voltage, as well as a reference input that you would select with a potentiometer to choose the limit of that. And I've just noticed this one here should be under voltage limit reference rather than over voltage, but fine. That then feeds into a latch circuit. So if one of the limits is exceeded, it will open the contactor and it can't be closed again until the limit is no longer exceeded and an operator pushes a button, just for sort of an extra level of safety. Then looking at multi-cell packs, again, pretty similar story, but instead of the protection circuit here, we're using that BMS to control the contactor. The BMS will have measurements for voltage, current, and temperature for all the cells, and that sort of thing should be provided by a manufacturer. And yeah, so hopefully you should know it's reliable. If it fails, either the power supply for it fails, in which case the contactor opens because there's no power to hold the contactor closed, or if it fails in terms of communication, the PC can detect a discrepancy in the data between the power supply and the BMS. Okay, so that's an overview of what we can do to help mitigate risk. So how about the negative impact of doing that? Well, it's largely cost. So you're looking at about £100 for a contactor, and again, £100 for a fuse. I've put those 100 amp, 500 amps there. So we're sort of talking about large format cells that will probably be in grid scale systems.
12 minutes, Tom.
Got it, thanks. And then for fire suppression, from what I found, automated fire suppression, you're looking at about £1,000 for a meter cube size enclosure. And then for a fire extinguisher that could be handheld, that's about £400 for a 9-litre one. But obviously that requires you being present to spot the fire. I haven't put the price of an enclosure there because it wildly varies depending on what you're getting, but I would tentatively say about £1,000 again per meter cubed enclosure. Aside from cost, negative impacts around impacting the experimentation you're actually doing. So contactors and fuses will drop voltage and can change the measurement from techniques like EIS. It's not a huge problem, but you need to just bear it in mind when parameterizing models and well, when doing EIS. Just to wrap up, in conclusion, there's some pretty simple steps you can take to improve the safety, and there's a real emphasis there on independent safety systems. There's obviously quite a big financial and time cost in implementing these things. And hopefully it's clear that this isn't covering every single battery testing setup, but whether each mitigation is worth applying is up to sort of an individual to risk assess it and decide whether what level of risk is worth doing, basically as low as you can reasonably achieve. That's pretty much it. That's just a reference for the diagram I used before. Thanks for taking the time to listen. Happy to take any questions.
Okay, thank you, Tom. Again, if you've got any questions, you can pop them in the chat. I guess you mentioned just in your conclusions then about having independent protection. Tom, when you've got a BMS system, yeah. Is that sufficiently independent, particularly if you're kind of driving the way that you're testing the cells from a separate PC?
Yeah, well, so the I'll just flip back to that slide if I can. Yeah, so what specifically thinking about some of the things I've actually been using, the BMS systems I've used, they independently control the contactor, i.e. they're measuring the voltage, and if something's wrong, the BMS itself will alert the contactor or turn off the contactor, and that has nothing to do with this communication. Obviously it's all to do with this communication bit, but then the PC should be able to quite easily detect any discrepancy between the power, what the power supply is reading in the BMS, and that's sort of how I've justified it as being independent. Does that answer your question?
Yeah, I think so. Yes. Yeah. So we've got another question there from Philip about fireproof enclosure.
Yeah.
But perhaps it's more of an observation about the amount of energy that's there, and perhaps that it might need to be explosion unfireproofs.
Yeah, I mean, it's something I'd quite like to test in reality, actually. We use quite heavy duty steel containers with fire suppression, but we haven't actually tested them, so I do. We have a site up at in Buxton that we've used for destructive testing, which I'd quite like to go to, but yeah, I think we're not allowed to at the moment with COVID, so yeah.
Okay, is there any questions from anybody else for Tom? If not, then I guess we can close that final session. And thanks again to all of the speakers.